Okie dokie, guys. Can you all hear me again? Can you guys hear me?
Yeah, we can hear you.
Good. Are there any questions or comments before we move on to the next topic? So what we want to do is we want to apply this martingale theory to price derivatives. So the underlying concept is the same as in the one period model. It's just now it's dynamic. And one thing that's more complicated in a dynamic world is simply just keeping track of all the indices, so bookkeeping. And so what's going to come now in the next few slides, this looks a bit overwhelming in terms of notation, but it's really not. Conceptually, it's not nearly as bad as it looks on paper. But we need to talk about wealth process, and what's called the self-financing. Condition. We already talked about these concepts in the one period model. So we have the wealth process. This is our xn. Right, so the way that the wealth process is defined is you look at the number of assets times their prices and you sum them up. So you look at the number of money market account units times the price of the money market account plus the number of stocks times the stock price. Right, so this quantity here, this is the number of bank units. This quantity here, this is excuse me. My allergies are acting up. This is the number of stocks, stock shares. So we take the respective numbers, multiply onto the prices, you add them up, it's going to give you the wealth. So we're going to say that the self-financing condition, this is when that's the wealth process. So the self-financing condition, this part, this is what you get here. The self-financing condition says that your wealth at time n can be computed using the holdings you have in the previous period according to this formula. Right, so these are the previous holdings, the previous number of bank units. This is at time n, right? So this is the number of bank units at time n minus 1, and the same thing with the stock. This is the number of shares at n. This quantity, this is the number of shares at n minus 1. We're going to say that it's self-financing if your wealth process value before rebalancing at time n is the same thing as the value after rebalancing at time n. That's where the word self-financing comes from. You're not allowed to consume, you're not allowed to receive income in this model. At least not yet. Okay, so now we're going to look at wealth dynamics. the wealth dynamics. So this will be my delta xn. This is equal to xn minus xn minus 1. So what I'll have here is I'll use the definition of what it means to be self-financing. I'll plug in the first one here into this formula, into the first part. So this would be delta n minus 1 is 0 times Sn 0 plus delta n minus 1 is n. That was my x. And then I'll have a minus. And then I'll use the definition of the wealth process at time n minus 1. So this is quite similar. The only difference is instead of n's here, I'll have n minus 1s. This is delta n minus 1 is n minus 1 plus delta n minus 1. So then I can combine. I can find a common factor. This can be combined into delta n minus 1 at time 0 times, and then it's going to be the difference in the bank account value, Sn 0 minus Sn minus 1, 0. Plus, I'll do the same thing for the stock. That was this guy. I have something over here, but now with a minus sign. Okay, so it came down to here. The first equality used the self-financing condition and the definition. The second equality, the last equality here, just combines the two expressions with the common factor outside. Then, what do I have here? Well, now I'm going to use the definition of what it means to have a multi-period binomial model. So let me just bring up that slide. Bank account, right? That's the one with 1 plus r. So if I move Sn 0 to the other side, I get that the change in the bank account is equal to Sn 0 times r. So that's the first expression I'm going to plug in. This here is going to be delta n minus 1 r Sn minus 1, 0. That's just a definition of the money market account. I'll leave the other term the way that it is. Then here I'll use the definition of wealth process. This here will be R. So I'll put R outside, and then I'll use that this is x n minus 1. I'll use the definition up here, but for n equal to n minus 1. So this was the term I had, so I need to subtract this one over here, but this one over here is going to get subtracted when n is replaced by n minus 1. It's minus delta n minus 1 Sn minus 1. And then I'll leave the second term alone. Okay, so now I can combine again. I will get, what do I get? I'll get r x n minus 1. And I'll have this delta n minus 1 outside on the other term, delta n minus 1. And then I'll have Sn. And then a minus, this is going to be 1 plus r. Sn minus 1. Okay, so this was a long calculation to get the wealth dynamics. Right? So the change in the wealth is where you are, times the interest rate, and then the holdings in the stock times the stock price. This is the random quantity, right? Because you don't know what the stock price is going to be over the next period. You know what the stock price is when you come in. You know what the wealth is when you come in, but the real random quantity is this one here. So this is the wealth dynamics. Now we're going to look at the discounted wealth dynamics, right? So we recall the discounted prices. That's why we found the martingale property. I mean, this is the one we're going to be playing with now. Recall the discounted prices. So we have S tilde N. That's going to be it's going to be the stock divided by the money market account. So I can now look at, and even if you want, you can also look at the discounted bank account prices, but these are trivial because they will be SN0 divided by SN0, which will always be the 1. But if you want, you could have these ones too. And then I can look at the discounted wealth. I can look at the discounted wealth. Look at the discounted wealth. So this will be my X n tilde. And they're going to be defined as Xn divided by the money market account. And so what we claim is, I claim that if I look at the dynamics of the discounted wealth, these dynamics here, they look the way that they do. But in the discounted market, you can kind of see that the interest rate is 0 in the discounted market. So you should get much simpler dynamics for the discounted wealth. It amounts to taking R equal to 0. So this term here is going to be gone, and this term here is going to be gone. All right, so what is it we claim? We claim that the wealth dynamics in the discounted market will be much simpler, and you'll simply just have this form. And the proof is not bad. Simply just work it out. So we start out with this formula. So I'll get from that formula, I'll get that xn is equal to, I'll move xn minus 1 to the other side, I'll get 1 plus r xn minus 1, and then this term. Okay, so I did nothing else. I moved this term here to the other side, combine it with r, I get 1 plus r there, and I get this term, and this is the same one. Okay, so now I have that, I'll divide by 1 plus r. And it gets to be a little bit easier. So 1 plus r will cancel out. I'll get xn minus 1. And then what do I get here is delta n minus 1 times, and then it'll be Sn divided by 1 plus r minus Sn minus 1. Okay, so now I can finally attack the thing that I need. I'm claiming that this equality sign here is true. I got what I have up here as my definition, so I'll plug it in. I'll say that delta xn tilde, I mean, this is equal to xn tilde minus xn tilde minus 1. And that's the change. I'll use the formula. How it's defined, this is xn divided by 1 plus Sn, the bank account time n minus xn minus 1 divided by the bank account time n minus 1. So this thing here can be worked out. There's a common factor. I can put out 1 over Sn minus 1, 0, put it outside. Then here I'll have xn divided by 1 plus r minus xn minus 1. So here again, I'm using that I get a price of the bank account at time n simply by taking the previous one times 1 plus r. And so now I can work it out because that's why we did the first calculation up here. Like I have 1 over Sn minus 1 is 0. And then I move this to the other side, I'll get delta n minus 1, and then I'll get Sn 1 plus r minus Sn minus 1. And this should do it. It should do it because here I'll have delta n minus 1. And so I'll have Sn divided by Sn is 0, so that was my S tilde n. And here I'll have minus S tilde n minus 1. So that's a long messy calculation. So if I look at the discounted wealth, the dynamics in the discounted market, so when I discount by the money market account, these are a bit simpler than the undiscounted wealth dynamics. You get one from the other simply by putting r equal to 0 in this more complicated formula. You get the other one, take r to be 0, we're just going to get delta n minus 1 times the price changes. And that's exactly what we see here. So, I mean, it begs the question, like, why on earth go through something so complicated? And the two pieces of calculations, well, it's because this is actually quite important. The reason we did this is because there's a martingale property hidden in here. So we can now use, S tilde n's martingale property. Right, this martingale property we can use, remember what it is Sn tilde conditional on Fn. This is exactly Sn tilde. To get another martingale property of discounted wealth processes. So that's why this is an important calculation. So I want to use this property here to get that martingale property. So what I'll do is I will start by computing. I'll use this property here, what we had on the previous slide. We get here x n tilde plus 1 conditional on Fn. This is the one that I want to prove is equal to x n tilde. Much like what you have up here. But here you have it for the stock. Now we're also talking about getting it for the wealth process. Okay, so we'll use the relationship between xn plus 1 and xn. Here you're going to get the change given Fn. So that's just the definition. That's just the definition. So what we'll do is we will plug in, well, xn is going to be Fn measurable. The wealth at time n, we know what it is at time n, so that will go outside. And then we'll have the more complicated expression, and this is where all the hard work is going to pay off. Delta xn plus 1, I need to replace n with n plus 1 on the right-hand side. I'm going to get delta n times the change in the discounted stock price. So this is the thing we have to compute. And we can use this rule that we had I think I already used it a few times today. Can use this property then. Can use this property then. If I have something that is already measurable with respect to what I condition on, that thing can just be pulled outside. Right? So this y here can just go outside the conditional expectation because it's already g measurable. And so that's what we see here. We have a product. We have a product. The position, my stock position at time n is already fn measurable. It can go outside. So this will be delta n times the expectation. Delta is n plus 1. Condition on fn. So what is the expectation in here? Well, of course, we have in here, this is Sn tilde plus 1 minus Sn tilde. But you see, when I condition, I can use the martingale property to say that the conditional expectation of this quantity is exactly that quantity. So when I use this property up here, and we call it star, just going to get Xn tilde. So this shows you that not only is the stock price discounted, a martingale under the tilde measure. Actually, what is true is that all discounted wealth processes, they are martingales under this tilde measure. Any questions on this calculation? I know the first few slides are kind of messy, but you have to go through it because this property here is a crucial one, namely that the wealth changes in the discounted market and your holdings in the stock times the changes in the discounted stock price. And it's that property that will take us from this equality to this equality. So that's why we went through it. But what it shows is that the discounted wealth processes, there is a martingale property that can, the martingale property of the discounted stock price carries over to the martingale property of the discounted wealth process. Are there any questions on this part? You guys are very quiet today. It's not a good sign. Are there any questions on this? Okay, then let's maybe try to make this more specific in a given binomial model. So what we want to do is apply some of this material to pricing a what did I write? A put option. If we look at a two period binomial, and let me specify the model by saying I have R to be 25%, and I have P tilde. It's the same thing as Q tilde. This is half. This is the model that we've been working with in a one period setting for a while. So you start out at 4, and it goes up to 8, 2, 16, 4, 4, and 1. Right, so what we want to do is we want to price a put. We want to price a put with strike, say 5. So what we need to do is, in a one-period model, you need the initial wealth and you need the stock holdings. The initial wealth and the stock holdings, such that at time 1, your wealth, this is equal to the puts payoff. That's the one that we've been doing in the beginning of the course. So now we're moving into something that's more complicated. We do a 2-period model. A 2-period model. So now it's going to be more complicated. You need the same structure. You need x0, you need delta 0, but you also need the stock position at time 1, such that your wealth at time 2 is equal to the puts payoff. So there's more stuff to be computed. And the difference is that up here, your initial wealth and your stock holdings, they were constants. And these things here, they were F0 measurable constants. And the same thing is going to be true here. These things, the initial wealth and the initial stock holdings, they are again going to be F0 measurable. But this one, the last one, delta 1, this is going to be F1 measurable. Namely your stock holdings at time 1, right? And your stock holdings at time 1 is going to depend on whether the first contract was heads or tails. Right? This is time 0, this is time 1, and this is time 2. So before you just had to figure out how much wealth do you need here and how and how many stocks do you need, such that at the end of the first period, the payoff of your wealth will be exactly the same as the payoff of the put. Now it's going to be more complicated because you start out with some position, and then at time 1, you're going to change your position in the stock depending on whether or not you went up or down in the tree. That's what is captured by delta 1 being F1 measurable. Okay, so let's try to do this. Let's try to do this. So what do we have? We're looking at, so the goal is to create these 3 quantities, 2 constants and a random variable. So we want it at time 2. You want your wealth. This is the replicating. Oh, I'm writing with the wrong color. At time 2, you want to replicate. So if you're looking at a put, with strike 5, that means that the payoff of the put is going to be 5 minus S2 positive part, right? This is the replicating property, and this is at time 2, right? Because we're imagining we're going to get in this 2-period model, we're going to get the puts payoff at the end, and the puts payoff at the end is going to be this guy here. Okay, so that's what we want to solve. And the way we want to attack it is we're going to use martingale theory. So we're going to look at this. This is the same thing. If I divide by the interest rate, so I did nothing else here than just divide by 1 plus r. And I did that because now I can use the martingale property, right? The martingale property for the wealth process the martingale property for the wealth process is something that happens for the discounted wealth. This is not going to work for the undiscounted, the one without tilde on top. So to get the martingale to get to use the martingale property for the wealth process, I have to change numeraire. I have to change the way that I measure my wealth, and I have to switch. I have to switch over and use the bank account as what I denote in. Okay, so then what? So now I have this relationship. I compute a conditional expectation, right? So I want to get that. So this is going to imply that if I look at x2 discounted, this is going to give me, under the tilde measure, if I condition on 1, this is going to give me exactly x1. Like, this was a martingale property of the discounted wealth process. Right, if this is not clear, maybe we should write it out here. This is the same thing as saying that e tilde xn plus 1 divided by Sn plus 1 0 condition on Fn, that this is equal to Xn divided by Sn 0. This is the same as canceling out. I get Xn plus 1 here divided by 1 plus R. Right, I'll use the relationship between the money market account at time n plus 1 and the money market account at time n. I'll use that relationship, pull it outside, divide over, and I'll have it here. Right, so this is not a martingale property of Xn. This is a martingale property of the discounted wealth. I have this 1 plus R that I need to keep track of. Right, so this is why that 1 plus R comes in here. But on the other hand, I also know that this is, I want to have 5 minus S2 as my payoff. So I'll get here 5 minus S2 divided by positive part divided by 1 plus R, give it F1. Right, so I'll have that, and of course I can go one step further back. I'll also have x0. This will simply just be the expectation of 5 minus S2 positive part, but now I have to go 2 steps back, so this will be 1 plus R squared. This will give me formulas for x0 and x1. But what I'm hunting is not just that, I'm hunting delta and delta 1. Okay, so let me try to get those. So if I work out what the right-hand side here is, so to get delta 1 as well as delta 0, we need to compute. So let me compute the right-hand side. This is 5 minus S2 positive part divided by 1 plus R given F1. So this is a calculation that we have done we've done something very similar to a number of times. The way that we attack it is, where's the randomness? It's sitting inside S2, right? S2 is not F1 measurable. So what we need to do is to replace this S2 with something that is related to F1. So we go back, we use the property. That so we can write S2 as S1 times the second coin flip, this psi 2. This is the multiplicative binomial model we're dealing with. So that means that S2 is given as S1 times this Bernoulli that models the second, this is the second coin flip. And then we have F1 here. Okay, so now what we do is we use the independence lemma. Here I have a complicated function. One variable is already measurable and the other one is independent. Okay, so we use the independence lemma. We use the independence lemma. What does it say? Well, it says you take out what's known. Okay, so that's my, it'll be 1 over 1 plus r. And then psi 2, this is either up or down, so I'll have a p tilde. And then I'll have 5 minus S1 and then up. Plus 1 minus p tilde. That will be S1. And then a positive part here. S1, it will be 5 minus S1 down, positive part. And of course, if you want, we can plug in what these actual values are. We had a specific model in mind when we started out. The specific model was that R was 25%. Okay, so the first quantity here, this is 1 over 1.25. And P tilde and Q tilde, were both equal to a half. Okay, so these two quantities can combine into a half. And then I'll have 5 minus S1. And U would be 2. Plus 5 minus S1. And then D would be a half. So this here would be my conditional expectation, right? And this is the thing that's going to be x1. So what we see is, we see that x1 is a function of s1. In other words, the wealth that you have at time 1 depends upon what the stock price is at time 1. That makes sense too. Okay, so this gives me a formula for x1. I also want, the goal is to create these delta 1 and delta 0. So how do I do that? Well, this is my formula that I want. This is my formula that I want. I want x2 to satisfy this. So to get delta 1, we need to solve. What do we need to solve? We need to solve this, the hedging equations. X2 is equal to 5 minus S2, positive part. And we have a formula for x2. We have a formula for x2. We have a formula here for x2. We're going to get that x2 is equal to 1 plus r times x1 plus x1 times this difference here. Let me write that out. 18. This here is the same thing as saying what? So we get it copied correctly. This is the same thing as saying that you have x1 times 1 plus r. What else was it? Delta 1 times S2 plus delta 1, this is S2, so it's a minus 1 plus r. This to be equal to, I want this to be equal to 5 minus S2 positive part. Okay, so we have two equations and two unknowns. Just as we did in a one period model, we get two equations in x1 as well as delta 1. What do we get? We have x1, 1 plus r plus delta 1. And then S2, there are two possibilities. It is equal to S1, and then you could either be up or down. So say that the first one is up, minus 1 plus r S1. This is equal to 5 minus S1 up. That was the first equation. If the second coin flip is up, what about if the second coin flip is down? Delta 1 S1D now. So we have that mess. These are two equations in x1 and delta 1. We have to solve. So we solve. Because we have two equations and two unknowns. They are very, very similar to the ones that we had when we were doing the one period model. We solve for delta 1 and x1. And if you do that, you're gonna get what? 1 plus r minus u, 5 minus s1 d positive part plus d minus 1 minus r, 5 minus s1u positive part. Everything divided by 1 plus r d minus u. And the same thing here. You solve for, this is my x. You solve for delta. 5 minus s1 u positive part minus 5 minus s1 d positive part divided by s1 u minus d. Okay, something like this is what you get. And as always, there is a sanity. Let's see. Again, check for sanity. We need to check that.
Hello. The x1 1 and r and theta 1 s1 d minus 1 1 and r s1. The place between this may should have a signal. Okay.
Was this the one I was missing?
Yes.
Okay. Yeah, there was a plus missing, right? Because what I'm doing is I'm taking this top formula here, and I'm sitting here at time 1. Okay, so at time 1, I'm looking at what could happen at time 2. Well, S2 can either go up or down, and so it can either become S1 times U or S1 times D. And so I'm just breaking this. Seemingly, there's only one equation here, but there's really two, because there are two possibilities for S2. So I plot, that's where I find S2, and this is where I find S2, and I plug them into the system. Solve, I get x1. But now we have two formulas for x1. So we're going to check that star, and then the other formula we had, wherever it is. We have two formulas for x1. Got to check that they're consistent. Where's the other one? It's here, right? We also had this formula for x1, this conditional expectation. That was the one we worked out here, right? This here is also x1. So let's call this double star. So we should check that star and double star, they agree. And they do. You can see here 1 over 1.25 times a half. This is very close to these p tilde and q tilde as 1 over r that you find here. And then you have 5 minus s1u, 5 minus s1u. You find p tilde in front of it. And here you find q tilde in front of the 5 minus s1d plus r. So these two formulas, they are consistent. So we can continue like this, and so now we have a formula for x0. You want to have a formula for delta 0 as well. Yeah. I'm not going to write them down in this generality. Maybe you just try to do the same calculations with numbers. Maybe do numbers. So. So we'll just try to work with numbers instead of these symbols. So with numbers, so I have my stock. This was 4, this was 4, this was 2, 8, 16, and 1. This was the stock. And then I have the put. This is the put. Put would strike 5. So what does the put pay out? We're given the payouts for the put out here, time always at the end. So we're going to get 5 minus 16 positive part, that's a 0. You're going to get 5 minus 4 positive part, that's a 1. You're going to get 5 minus 1 positive part, that is 4. Right, so the first goal that we're interested in is pulling these payouts back to time 1 and then pulling them back to time 0. Right, the goal is to figure out what to put out here at the root of the tree. So we now have these two payouts and we have these two payouts. So the first thing we do is we pull them back. One period. Always start from the right and move towards the left. Right, so we have time n equal to 1 values. So wealth. We have an upstate. So that's up here. We have downstate. So what's the wealth in the upstate? We'll be looking at this payoff, 0 and 1. So we're going to be looking at p tilde times 1 over 1 plus r times 0. That's that 0 plus 1 minus p tilde times 1 over 1 plus r times 1. So that's going to be the wealth. This is equal to, if I do it correctly, this is 1 over 1.25. Right, so we're looking at what is the value in this node here of getting that payoff at the end. That is 1 over 2.5. And likewise, if I move on into the downstate, I'll have p tilde 1 over 1 plus r times 1 plus 1 minus p tilde times 1 divided by 1 plus r times 4. So this is of course a much bigger number. And if you work it out, it's 2. So this is 2 down here. So that was the wealth. Now we can do the replicating. The replicating portfolio. So if I am in the up state, I want to know how much I should be buying up here, how much I should be doing down here. So we use the formula. We use the formula we have up here. What will it be? It will be 5. It will be what? It will be 5 minus, if I am up here, the stock price is 8. 5 minus 8 times 2, that's 5 minus 16 plus the part that's not there. So this is, right, this here is my x1. This here is my delta 1. So in my up state, I will have, the first one was a 0, minus, and then what's the other one? 5 minus, and then it's S1. Times 8 times D was a half, so this is 5 minus 4, that's a 1, divided by, and what downstairs is S1, this was 8. 8 times U minus D. U minus D, this was 2 minus a half. I think, yeah, that's what we get. This is equal to minus 1 over 12. And so if I am in the down state, what's my delta? Same formula. Same formula, the only thing I have to change is what S1 is. Instead of S1 being 8, S1 is now just 2. So I get is 1 minus 4 divided by 2 times 2 minus a half. Okay, this is minus 1. Right, so the wealth that I'm going to be needing here is 1 divided by 1.25. This here is 2. This is my x of, I get a tail, no, I get a heads, is equal to this, x1 of tails is equal to that. And likewise, I'm looking at delta 1 of heads, this is equal to minus 1 over 12. If I'm looking at delta 1 of tails, this is equal to minus 1. So now I know what the values are here, and then I need to move them out into the root. Okay, so how do I move them out into the root? Well, I move these two payouts out here, and I do the same sort of calculation as I did before. So let me try to do that. So the values at times 0, I'm going to get wealth. So this was my x0. How will I do that? Well, I have these two, 1 over 1.25, and I have 2. I need to move these two values over here. So I discount them. And look at the probabilities. That was 1 over 2.5, 1 minus p tilde, 1 over, what was the other one? That was a 2. Work this out right. It's 2.4 divided by 2.5. And I get the portfolio, the replicating portfolio. So this is my delta 0. What is that going to be? Be the same formula as before. Delta 0 will be, this is my x0. It will be the difference out here. So 1 divided by 1.25 minus 2 divided by, and then we need the initial, what does it we divide by when we get delta? Divide by S0 times U minus D. S0 was 4, U minus D, this was 2 minus a half. This is minus 0.26667. So now we can fill in the rest of the tree. The initial wealth is 2.4 divided by 2.5. This is my x0. My delta 0, this was minus 0.26667. So now we have the tree completed. If you're looking at getting a payoff at time 2, which is equal to 0, 1, and 4, the way that you do it is that you move the payoff back one period, and then there'll be two possibilities depending on what the stock is. If the stock goes up, you're in the top part. If the stock goes down, you're in the bottom part. So now we're going to get these two random variables, and then you discount by the money market account. That's going to give you a martingale. So compute the expectation is going to give you x. This is what happens in a two-period binomial model. Right? But the key insight is like so key steps. You're looking at key steps. Right? You're looking at, say, if you're in a multi-period model with n periods, what you want to have happen is you want to have a wealth process such that at the end you replicate. Right. This here is the payoff. This is the payoff of the derivative. And this is at time at the end. Right. So you're all the way out here to the right in the model. Out here, all the way at the end. This is where the payoff of the derivative is prescribed. This is your f of SA. Now the question is, how would you value this payoff at earlier times? In particular, how would you value it out here at time 0? Okay, so the way that we're going to do that is the same as in the one-period model. We will construct a wealth process. We'll construct a wealth process such that by trading, we're going to get to exactly the same payoff as the claim. Right? So we've got to construct. So to get this to work, right, we need to construct. We're going to construct the initial wealth, and we're going to construct the initial stock holdings. Then we're going to construct the holdings in the stock at time 1, all the way up to time n-1. Right? So it's our job to create these. We need to construct these such that the wealth that you're going to get out in the end, such that xn equals this derivative here. And the question is, how does one do that? Like how does one construct this replicating portfolio? Well, you We use martingales. This here is the same. So I'm basically redoing some of the calculations we just did before. Right? This is the same. This is the same as discounting. This is the same as discounting by the money market account. So then use that this quantity here as a martingale under P tilde. And then if I have that, then this is going to imply that x tilde of xn given f say n minus 1, this is going to be the same as f of Sn divided by Sn given Fn minus 1. If I have this property, I can pull it back once, and then I can use it as a martingale. And I can use this as a martingale. This is exactly xn minus 1 tilde, because I know that discounted wealth processes are martingales. So this is going to give me a formula for the wealth at the end, at time n minus 1. And likewise, I can, the thing I have on the right hand side, I can actually compute what this is. I can compute what this is. This is what I have on the right hand side. Here I have the bank account. There's nothing random about it. He can go outside. This is Sn0. And then I have a conditional expectation of f, and then I can make the connection between the stock price at time n and the filtration at time n minus 1. This is equal to Sn minus 1, and then you need the coin flip as psi n given Fn minus 1. Okay, so this here is equal to, I now use independence, between the nth coin flip and the previous coin flips. This is going to give me 1 over Sn0. And then what do? I have P tilde times F, and then I'll have the stock price over here. Psi, this can be a U, probability P plus 1 minus P tilde times F Sn minus 1 times D. Right, so that was the independence lemma. So I really get a formula for the wealth. This is a formula for the discounted wealth. So if I want to have the undiscounted one, I need to relate the discounted one with the undiscounted one. Of course, I can move the bank account to the other side. Now you can see most of it cancels out. This here will just leave me with xn minus 1. This is going to be equal to 1 over 1 plus r times this mess over here. So this gives me a formula for the wealth process. And as you can see, what I have on the right-hand side, this is a function of Sn minus 1. Right? This here is a function. Let's call it Fn minus 1 of Sn minus 1 for the function Fn minus 1 of x defined as 1 over 1 plus r p tilde f of x times u plus 1 minus p tilde f of x times d. Right, so it's really true that the wealth at time n minus 1 is given as a function of the stock price at time n minus 1. Okay, so that's how we go one step back in the tree. So we moved from far out here, we moved one step back. And so of course we're gonna keep doing this. So we'll move one step more. So we will go one more step. So we will iterate. We'll iterate. So we're going to be looking at what does xn minus 2 look like? Well, how are we going to do that? Well, we're going to move. So xn minus 2, we're going to look at the conditional expectation. So we're going to use that xn tilde is a p tilde martingale. So if I look at xn minus 1, conditional expectation, but now I'm going to move it back one more. This is going to give me xn minus 2. So here we had xn minus 1. I'll plug it in. This is the same as, let me use this function I had here. This is the same as if n minus 1 evaluated at Sn minus 1. Right, that was this expression here. This is my xn minus 1. So I want this, I want to be able to compute this conditional expectation. But that goes exactly like it did before. This goes exactly as it did before. I will compute, what will I do? I'll compute my xn here. I need xn tilde. So I should be more careful here. That's not quite right. I need to divide here by 1 plus r, right? This one here uses that xn minus 1 is equal to fn minus 1 of Sn minus 1. So if I want to get the tilde one, I need to divide. And so how would I compute it? I would use the same argument as how did I go from here to here? Well, it's very similar. How I would do 1 over 1 plus r, 1 over 1 plus r, and then I'll have p tilde fn minus 1. Sn would be Sn minus 2 times u plus q tilde 1 minus p tilde fn minus 1 Sn minus 2 times d. Right, so that would be my xn tilde, xn minus 2 tilde, and that's the same formula as before, and you can keep going. This here will give you a bunch of functions. This here will give you it gives you functions f1 of s1, which is equal to x1. It'll give you f2 of s2. This will give you x2, and so on. But of course, you also know that. So how would we get? So now we have these functions. So how do we get the deltas? So using these, this equals all the way down to fn minus 1 of sn minus 1. This is going to give you xn minus 1. That was the first one we started out with. That was this guy here. This mess in here was the last one. So given this, how would we create, given these functions, given f1 up to fn minus 1, how do we get there's also this, there's an f0 here. Given all these functions, how do we get the investment strategies? And so this is where the how do we get example? How did we get delta 1? Well, we had to solve these equations. Yeah? And when we solved for them, this is what we got. I'm hunting all these deltas here, and I'm saying that given these functions, we can actually get them out. We do it. So to get, for example, the first one, we would use that. To get the first one, we would use that. Well, on one hand, you have that f of s1 is equal to x1. So that was this one. So just expand out. This is equal to x0 times, what was it, 1 plus r? Plus r plus delta. Plus delta 0 times what is S1 minus 1 plus R is 0. And then we expand out. The randomness comes from S1, it's here and here, so you have basically two equations. You have F1 of S0 times U, you have F1 of S0 times D. You'll have X0, 1 plus R, delta 0, S0U, minus 1 plus R, S0. The same thing down here. So now we solve. We solve for x0 and delta. And then you do the sanity check. Sanity check that x0, that solution you're going to get is exactly that. That function that the function that you have over here as well. This can seem, I don't know how many of you could follow all this, but this can seem pretty overwhelming, but it is really not. It is not that horrendous to create these functions. An example of how one could do this if you switch away from puts and calls, if you look at a payoff function, f of x being, say, that if you pick something like a square root, then what you would have to do, how would you find these many functions? Well, you will start by computing the conditional expectation of f of Sn discounted. That will be the first one. And how would you do that? It would be 1 over 1 plus r, conditional expectation square root Sn minus 1 times that psi, given Fn minus 1. So you're ending up here with 1 over 1 plus r, that square root comes out. And then you'll have p tilde, square root of u plus 1 minus p tilde, square root of d. So this here is your function. This is your, this gives you the last one. So f n minus 1 of x is equal to 1 over 1 plus r root x times p tilde root u plus 1 minus p tilde root d. So that was the last function. So how do you get the previous ones? Well, you roll it back one more. So to get fn minus 2 of x, you do the same calculation. But instead of f here, you'll use fn minus 1. So you're looking at e tilde fn minus 1 of sn minus 1 divided by 1 plus r, condition on fn minus 2 this time. How to work it out? E tilde. This long function has to go in there. You're going to get 1 over 1 plus r squared. You're going to get a square root of Sn minus 1. And you're going to get another constant, p tilde square root u plus 1 minus p tilde square root d, given fn minus 2. So you can pull it all outside. 1 over 1 plus r squared. Here there's a coefficient p tilde square root u plus 1 minus p tilde square root d. And then you're stuck with the randomness again, but it's very similar to the randomness you had before. This will be square root over Sn minus 2, and then the expectation of root of psi n minus 1. Like in this quantity here, this is p tilde square root u plus 1 minus p tilde square root d. And you see this is exactly what you have over here. And so you combine the two things, 1 over 1 plus r squared p tilde square root u plus 1 minus p tilde square root d. Now squared times the square root of Sn minus 2. So your next function. So fn minus 2 of x is given as this mess up here. Square root x 1 over 1 plus r squared p tilde root u plus 1 minus p tilde root d squared. As this is how we create all these functions. You see, got the first couple created. So fn minus 1, this mess, fn minus 2, this mess. And you can now recognize the pattern probably that if we were to compute fn minus 3, well, fn minus 3, this is, you're going to get a higher power here, but it'll still be a square root. So you can keep going here, and ultimately you end up with f0 of x. This is probably going to be square root of x, 1 over 1 plus r to the power n p tilde root u plus 1 minus p tilde root d to the power n. This here is your initial wealth. x0, this is f0 of s0. So if you were to price, a claim that pays out square root of the stock, you use this formula here, but you plug in the stock price for x. Okay, I know this is a lot to take in. There's a lot in today's lecture. I don't doubt that. So we'll do some of this stuff again. In tomorrow's TA session, you're also going to be playing with a bunch of examples, like the last one we did here. I think this last one we did here, this is actually in tomorrow's tomorrow's TA session. Okay, and I went over time. Are there any questions or how far did you guys hang on to? Are there any questions before we say goodbye? You got a little bit rusty in the end. I'll recap on that when we start up next time. I'll see you guys. Office hours are Thursday and Friday mornings, and otherwise I'll see you next Tuesday. Have a good night.
Thank you, Professor.
You're welcome.